In this video, I will show you somewhat qualitatively, conceptually, how to use the energy conservation principle to prove Bernoulli's equation. So the focus will be we're going to see how we can think of Bernoulli's equation and how we can conceptually derive it from energy conservation. At the end of the day, Bernoulli's equation is just energy conservation applied in fluid. Now, this is the fluid that I have here, okay, and you can think that this is perhaps water. It is flowing on a pipe, and the pipe is changing heights. So here initially, let's say the flow goes this way. Initially, the fluid is flowing at a low height, and then it's going up, and then it's flowing at a greater height. It is also, the pipe also has different diameters. So here it is more wide, here it is, the cross-sectional area is smaller. And of course, as a result of the change in height and the change in diameter, you probably will have a different speed. Now, when we talk about energy conservation, we start with the change in the energy of the system is equal to the external work done plus Q. Now, we are assuming that there is no thermal energy transferred between the system and the surroundings, so that would mean probably that there is no friction or not much friction between the fluid and the pipe. Okay, we need to make that assumption. And also, for a system here, I will define the system to be the earth and also this part of the fluid. We have seen that we will write the change in the energy of the system as delta ER plus kinetic plus potential. And we have also seen that there may be some change in the internal energy. There is none for the phenomenon that we are studying, and this is the external work done. Now this will be the work. Let's make this to be 0.1. Let's say that this is 2. So by 1, I mean here. By 2, I mean here. This will be the contact work that is done from the surroundings. Now, because the system includes the earth and this part of the fluid, 1, which with 1 I mean here, this part of the fluid is part of the surroundings and it is pushing on my system to the right. This part of the fluid is part of the surroundings and is pushing on my system to the left. So there is some work done from 1 on the system plus some work done from 2 on the system. Now we are not dealing with change in the rest energy. So I have EK final of the system minus EK initial of the system plus EP. Now for EP, of course, I'm referring to gravitational between the fluid and the earth. And I will just copy the same 2 terms for work. Nope. Now, of course, I will assume that the kinetic energy of the earth is not changing. It's only the kinetic energy of the fluid that is changing. So this will give me 1/2 the mass of the fluid times the speed final squared minus 1/2 mass times the initial speed squared. We know that for the gravitational potential energy, we can model that as the mass times g times y final minus m g y initial. Now, this part of the surroundings, this part of the fluid, as I said, is pushing on my system to the right. And I want to remind you that there is a relationship between pressure and force. And if I assume that my system moves to the right, is displaced to the right by a little bit, let's say here it's displaced by delta x1 and here it is displaced by delta x2, then this part of the surroundings is doing work that is equal to the force that one exerts on my fluid, or the pressure at 1 times the area at 1 times delta x1. And this is a positive work done because this part of the surroundings is pushing on my fluid to the right, and this fluid is also moving to the right, minus P2 A2 times delta x2. And the work that this part of the surroundings is doing on my fluid is negative because the fluid is moving to the right and the force that this exerts on the fluid is to the left. So the force is opposite to displacement, and in those cases the work is a negative number. Now, I can rewrite, I can say that for the mass, I can write that as the density of the fluid times the volume of the fluid times the final speed squared minus 1/2 the density times volume times the initial speed squared. I will do the same thing. V G Y final minus the density volume G Y initial, and I can move P1. Now take a look here. I have the area times delta x, so the area times delta x1 will give you the volume. And then I will have plus P2 also times the volume is equal to 0. Now I have used final and initial, and I can make the final to be at point 2 and the initial to be at point 1. Now, one thing I can do easily, you can see every single term here includes a volume. So that means I can get rid of the volumes. And I can rewrite whatever is left. I will write it again. And now for final, I'm going to use 2, and for initial, I'm going to use 1. So this will make it 1/2 the density times the speed at 2 squared minus 1/2 the density times the speed at 1 squared plus the density G Y at 2 minus the density G the Y at 1 minus the pressure at 1 plus the pressure at 2, and that is equal to 0. This is Bernoulli's equation. I do need to mention my proof could have been more rigorous. My goal though here is not to go over every single thing in that in proving Bernoulli's equation. Rather, my goal here is to show you that Bernoulli's equation is essentially an application of energy conservation when you work with fluids. Bernoulli's equation does not include any new physics. The term that is 1/2 density times speed squared, this is the kinetic energy of the fluid. When you see this term in Bernoulli's equation, this comes from kinetic energy. When you see the density times g times y, this term in Bernoulli's equation, this represents the gravitational potential energy between the fluid, your system, and the earth. And the term that only includes the pressure, this originates from the fact that you have some work done from the surroundings to your fluid. And this is Bernoulli's equation, just an application of energy conservation to fluids. And I want to remind you, when we started this section on fluids, I mentioned that with fluids we don't really use forces, we use pressure. This is why in Bernoulli's equation you see pressure. And we don't use mass very much, but rather we use density. That's why in kinetic energy and potential energy you see density, not the mass. So just with fluids, it is more convenient to work with pressure and density rather than with forces and mass.